Have you ever wondered how robots deal with extremely noisy data? As we drive along, we have seen that lanes don't always appear perfectly. Yet, our self-driving cars are remarkable at finding these lanes despite harsh conditions, despite dust on the sensor, despite the lanes being broken. In today's episode, let's demystify how that can be done using a very powerful technique in mathematics called RANSAC. So let's dive right in. Let's say we want to fit lines to the image points to find a lane. Let's start with a very simple high school problem. If you have a single point, what would the line be which passes through this point? The answer is fairly simple. You can say, hey, I'm going to draw a line which passes through this point, right? And this is perfectly correct. But another person might say, hey, like I can draw another line which is slightly different from the first line, and this is also correct. And you would be absolutely correct. And a third student or a third person can say that there's a third line which can pass through this. So as you can see, we have infinite number of lines which can pass through this single point. This is what we call in mathematics as an under constraint problem, and it has infinite number of solutions. So as you would know, if you are trying to draw a line, we need a minimum of one point, which is this, and you will get infinite solutions. What happens if I draw another point? This is what you would have seen in your school, in your middle school or your high school, where you're asked to fit a line through 2 points, right? And if I ask you to do that, the answer would be very simple, wherein you would draw the line which passes through both the points, or you would join a line which has these 2 points at the ends. This is what it would look like. And you can write this in the form of ax plus by plus c is equal to 0, where you would fit in the values of these points x1 and y1 and x2 and y2, and so on. And you would basically find, using Cramer's rule, the values of a, b, and c. And this is what we have done in the high school. This is called a perfectly constrained problem, which has a unique solution. Okay, now let's think about another problem wherein we have a third point. So what would the line be which passes through these points? One of you might say, hey, I'm just going to pick these 2 points and I'm going to call it a day. And you would be fine, and this is not wrong. Another one might say, I'm going to pick a different 2 set of points, and so on and so forth. And this is also absolutely correct. But if I say that, hey, I want a line which is quote unquote optimal, which essentially gives me the best solution for all these 3 points, right? What would that look like? Intuitively, it might look like something like this, wherein it doesn't really pass through any of these points, but it tries to minimize the distance between these points. In other words, if I drop a perpendicular from this point to that line, it's trying to minimize this black dashed line for each of these points on an average. I'm going to call this di. So if you want to get really mathematical about it, I'm trying to find this value of a, b, and c, which gives me that equation of the red line. And that's what argument says. It's like, give me the arguments a, b, and c, which minimizes this function. The minimization function is the sum of squares of distances of each of these points to that line, right? And that's what we are trying to do for all the points on an average. Great. And instead of dropping perpendicular to the line, we can also drop vertical perpendiculars, and it's going to look a very similar way. Okay. This in machine learning is called linear regression or ordinary least squares. And this is of the form ax equal to b, and it can be solved using this formula x equal to a transpose a whole inverse a transpose b. And this is what is called an over constraint problem, which means that you have more data points than you would require for the parameters of the solution, and you're trying to find the least square solution here, because we are doing the squares and we are trying to find the least the values of a, b, and c are the model parameters, which minimizes this loss function. And this unique solution can be obtained through minimization of the problem, in this case a linear least squares. And we are minimizing this heuristic, and it's also in the land of neural networks, which we will talk about in the future episodes. So like, share, and subscribe and stay tuned for that. Is called the loss. Okay, what happens if we have a lot more data points, right? It would be the exact same thing, because in the previous example, we did not say that it needs to have 3 points. As long as it's more than 2, and the same method will work. Okay, what about a scenario like this where we have a lot of outliers, right? So, or we have one outlier wherein the outlier is really far away. If we just take the same averaging method we did before, the line will be skewed towards that outlier. And the farther this outlier gets, the worse our estimate will be, right? And it's like one bad apple spoiling the entire bunch, right? That's the goal. So what we can do in the land of machine learning, we can say we can regularize this term. So in other words, we say that, hey, if the values of A, B, and C become really large, we want to penalize for that value of A, B, and C. So what we are going to do is we have our standard minimization of least squares, but we also add a penalty term which says, okay, if the values of A, B, and C get really large, this is a bad solution. Remember that we are trying to minimize. Adding this term of the A, B, C like norm essentially is going to increase the value of this loss function, which is basically saying, hey, this is bad. So this penalizes for the values of large values in the model, which is deviating that line from the actual line. So the penalty again can be in the form of any norm. In this particular case, it is a sum of squares, but we can have an LP norm in math. An LP norm in math is defined for a vector x this way, where you take each element to the pth power, you add them up, and then you take the pth root of that. So this helps you alleviate different kinds of noise. And what I'm showing you here is like the unit circle, wherein like in that norm, what would a distance of 1 look like? As you would expect, at p is equal to 2, it looks like a circle because it's x square plus y square is equal to 1. And for the blue line, which is the blue curve, you see the norm p equal to 1, which is basically a rhombus. As you get closer to infinity, you will approach a square. As you approach to 0, you will approach a plus in the middle. The same thing can be extended to 3 dimensions, and this is what it would look like. Great. So with p is equal to 2, this is the solution you would get, and with p is equal to 1, this is the solution you would get. So essentially, the sensitivity to the outlier is controlled by the value of p. The higher the value of p, the more sensitive it would be to the outlier, but it can also follow the data along much better. The smaller the value of p, the less sensitive it is to the outlier, but is also less sensitive to the data itself. So as p goes down, you reject also the variation in the signal. So there is a careful trade-off between sensitivity to changing in signal. If there are subtle changes in signal, you want high sensitivity, but that will also come at the cost of high sensitivity towards the outliers and the robustness to noise. So if you have informed decisions about what kind of noise there is in the system, we can choose a p appropriately. Great. So what happens if there are too many outliers? Let's say we have about like 30% outliers or 20% outliers. That's a lot. Even with regularization, our results are not going to be that great. So how do we deal with something like this? So what we can do is, remember the first example we talked about wherein we had 3 points and then we picked 2 of them and then we fit a line to it. We are going to follow a similar ideology, but we are going to take that to the next level. So we are going to start with the minimum number of data points that is required to fit a model. Since we are fitting a line here, we are going to pick 2 points, and these 2 points are going to be picked at random. There's no craziness involved in this. So it's going to be these 2 yellow points which we have picked randomly. We are going to fit a line to this, and then we say, oh, hey, like we are going to draw a distance from this. In this particular case, it's going to look like a rectangle. And we are going to count how many points actually end up in this rectangle, which means that it's a good fit. So in this particular case, we get 3 points which are in this rectangle, green rectangle. We are going to call this the inlier set. So we are going to count the number of inliers. So we're going to repeat this again and again. So we're going to pick 2 more points. And so in here we find number of inliers as 4. And then we are going to pick these 2 points and we are going to find the number of inliers as 5, right? Beautiful. So this is the max number of inliers we have found. We can keep running this algorithm for a few hundred times, or we run it until a percentage of the total number of data points becomes the inlier set. And then what we do is we pick these 5 points again, and then we fit the least squares line again, and this is going to be the final estimate. Remember that the same ideology can be used to fit any complicated model. In this particular case, we are doing a simple straight line fit, and we will extend this to something in a few seconds. This is called random sample consensus, or RANSAC, and this was introduced by SRI International, Stanford Research Institute, which has done pivotal work in a lot of different domains, including robotics. And this is the paper which is from 1981. It's a great paper. I would urge you to read that. So in the era of deep learning, you can basically take the same concept of RANSAC and you can model this into a neural network, and it's called differentiable RANSAC, right? And in this particular paper, they show it for camera localization, and it's called DSAC. And I would urge you to read this as well. In one of the future episodes, we are going to dive deeper into DSAC, so stay tuned for that. So now what we want to do is, remember that when we did feature matching in the previous episodes, the features, despite our best efforts, does not always match perfectly. So most of the features match well, but we have a bunch of outliers. We could have like 20, 30 or 40% outliers. So what we want to do is we want to find the best possible solution for homography if we want to do panorama stitching or something like that, or to find odometry. So we want to basically find the transformation between the two images, assuming they are a plane. So what we are going to do is we are going to say, hey, we have feature matches, we have 4 points, and this is what it is going to look like. So the score is essentially like what we are trying to essentially do is like we are trying to find the inlier set. Remember in the previous example, we said, hey, it has to be within that green rectangle. That is represented as the score, which is the pixel difference after projection, which is also called as reprojection error. This is one of the most important concepts in computer vision, wherein you take image 1, you apply a model to that image, you're going to transform that points, and you're going to detect the same set of points in image 2, and you're going to find the difference between them. In an ideal world, if the model is perfect, the reprojection error should be exactly 0 pixels. But because of noise, it won't be exactly 0. We are trying to reduce this by making our model better. That's what we will do here. So the RANSAC algorithm will be as follows. So we need the minimum number of points to estimate the model, which is homography, which is 4 points from the previous episode. If this is not ringing a bell, please go back to the previous video and watch that. And then what we will do is we will use the 8-point algorithm to compute the homography. And then we take that homography, we apply it, and we say, hey, like how many of these is the inlier set, which is using the reprojection error. And we are going to have some pixels, let's say 2 pixels or 3 pixels as the reprojection error tau. And we are going to say that is equivalent to the green rectangle we were seeing before. And you're going to keep repeating this until you find enough inliers or exhaust the number of iterations. Once you find the inlier set, you compute the homography again, and basically that gives you the final homography matrix. Great. So just to recap, how would you fit a line through 4 non-collinear points? How would you deal with very few outliers? How do you deal with large number of outliers? How do you use RANSAC for estimating robust homography? See you next time. Take care. Bye-bye.